Yeah. So as few of
Yeah.
yeah, I think it. Yeah, as few of you guys had asked earlier, right? Ki, how can you visualize this, and it would be better if you could see what is happening, right? So this is exactly what TensorFlow team thought, and they developed a website which is called TensorFlow Playground. And here you can play around with multiple different things. Okay, so Sanket, would you like to start this?
Yeah, I'll start with it. So basically, this is the place where you'll get all your doubts solved. Earlier, I saw there were a lot of doubts saying that does number of neuron, like how, what should we do? Should we increase the number of layers, or should we increase the number of neurons, or what? Which function when should we use? So all of these doubts that you have, you can try out yourself here. So this is the TensorFlow Playground interface. So basically here, this is our basically neural network. Here we can have the number of inputs as features. Now, one thing you should know that every neuron has a represents a particular feature. So suppose this is going to be a classification. So we'll select the problem type as classification. Then the learning rate, we won't go into details of that. Activation functions, we saw that there are different types of activation functions. So here you can try why non-linear functions we should be using and why we shouldn't use linear functions. So something you can try it here. Then this is the, as I said, this is the input layer. This is our hidden layers. So basically you can change the number of hidden layers to 3, 4, and in each hidden layer you can increase the number of neurons also. So just for we'll just keep it as 2, and this is basically our outputs. So as I said that each neuron has a particular feature. So basically here this so we are giving some input, and if you consider this as the neuron, so this neuron has this feature that it is classifying it is trying to classify in a slanting line. Okay, that is the particular feature of that neuron. You can see this that this neuron has this feature, and this neuron has this feature that the line is slanting in this other direction. And then these are basically the weights that you can click and check the weights also, and this is basically our outputs. And epochs is, as I said, it is the number of iterations. Also we had some question related to number of iterations earlier. So now we'll just start with we'll check about what happens if when we take a linear activation function. So I select the function to be linear. The classification
Just before starting, for you guys, once on the left side, you can see data, or you can select different types of data sets, and on the right side, you can see that those data sets are being plotted. So orange color denotes that data point belongs to class A, let's say, and blue point denotes the data set belongs to class B. So there will be these are two different points that we need to separate, and we want a function that will act as a decision boundary between these two classes, right? So this is what our aim is. And yeah.
Okay, so we'll select this type of data set. So all the blue points are of type A, and the orange data points are of type B. So we are, for this example, we have two hidden layers. One has 5 neurons, and the second one has 2 neurons only. And the activation function here we are going to use is linear. So we'll just run the we'll just start the network, and we'll see what it classifies. So you can see that if we keep the activation as linear, the output we are getting is kind of linear, right? So basically the input was it was trying to classify all the points to the right as blue, and all the points to the left as orange. So we see that the output that we are getting here, it's trying to classify these lines. You see these, it is basically telling that the output we are getting is kind of linear only. And suppose now okay, so it has become we have graduated some 500, 600 iterations. I'll stop it, and now we'll see what if I change this function to linear. Will it be if I change the function to some non-linear function? We'll take the ReLU function. We'll see what happens if we take a non-linear function. Does it classifies does it classifies those points properly or not. So we'll start it. Yeah, you saw how it classified the data points as the function was non-linear, so it was able to classify the distinguish the blue points from the orange points. So that is basically what happens when you have activation which is non-linear. If we try to get a linear activation function, then what happens is that output is also again some linear combination of the weights and inputs that we take. And if we take a non-linear activation function, that's when we can solve complex problems, as in here. Suppose I take again linear. So you see the output is again some linear combination. It is trying to classify the example linearly. So you see how it is, the output is basically some linear combinations of our features. And we saw that each neuron represents a particular feature. So this is the feature of this is, you can see in the right hand screen, this has some another feature, this neuron has another feature. Again, you can see what happens when you increase the number of neurons. So for that question, we'll just take a proper example. We have a sigmoid, and again the question is this. We'll just keep number of neurons to 4, and we'll increase the number of layers. So let us have 5 examples. We'll see what happens, and we'll do this. So you saw how slowly our network is doing, right? Now this is going to take a really long time. See, also we saw that how sigmoid, it takes time because we have to compute 1 upon 1 plus e to the power z. You can check here yourself that if we increase the number of layers, or what happens, and what if we increase the number of, you saw that, you are seeing it, right? It's taking so long to just classify the problem, and we had the same example that was there earlier. It classified it in seconds. So now let us do that. We'll just get back to the 2 hidden layers. Now we'll let it be sigmoid only. We won't keep at sigmoid, okay? We'll let it be as ReLU only. As we said that we tried to use ReLU and not sigmoid. We'll do the same example again. It's taking example. Okay, so you saw it took some time. What if increase the number of layers? You can see, try it of yourself. What if increase number of layers? So the last count is 6. Now we'll just keep it as 1 layer, and we'll increase the number of neurons. Reset it, and then let's see. So you saw that if we keep the layers 1 and increase the number of neurons, our model will better. So you saw it in iterations, like in this much iterations we got it here. And the same thing if we had done using lot of layers, how much time it was taking, and the iterations were also slow. 6 hidden layers. So basically you get it, right? No, just increasing the number of layers wouldn't do any wouldn't make our model better. It would make it slower. Yeah, see, it took time to get to the output. But if we try to increase the number of neurons, that may make our model predict faster and accurate. But then there's also this concept of overfitting, underfitting that comes into picture if we increase the number of neurons too much. So which we'll be learning right now in the next session. So this is all. Mihir Bhaiya, you want to add something? You guys can check out this.
I guess you explained most of the thing. Yeah, that will be great if you send them the link. You can try this out on your PC as well.
Yes.
Yeah.